My name is Kelsey, and today we're going to be telling you all the story about our friend Oscar and how he improved his tennis strokes using dynamics.
As you can see, Oscar's having trouble getting his balls over the net until he looked in his dynamics book and he came across linear momentum. Now, linear momentum is mass times the velocity of the mass center. And these are the units, kilogram meter per second and slug feet per second. Now, linear momentum has its direction defined by the velocity of the mass center. And as the name suggests, it's in a straight line.
The second concept that Oscar took a look at was angular momentum. And as William just explained, linear momentum has to do with objects that are moving in a straight line, while angular momentum has to do with objects that are rotating. Angular momentum can formally be expressed as the moment of the particle's linear momentum about the mass center of the body, which is represented by this equation, with r being the distance between the object and the mass center, and p being the linear momentum, which we just saw the equation for. This can also be expressed in terms of the moment of inertia times the angular velocity. And as we are all familiar with the moment of inertia, we are usually given values for the moment of inertia based on the shapes that we are given. Also, the units for angular momentum are kilogram meter squared per second. So angular momentum can be applied to three cases: translation, rotation about a fixed axis, and general plane motion. For Oscar's case, we'll be using this application of angular momentum: rotation about a fixed axis.
So when I use conservation of linear momentum, what happened when I was hitting the ball is just it was a linear motion, and as you can see in the equation, I was using the mass of my arm plus the mass of my racket, that's ma, times the head speed, which was equal to the mass of the ball and the velocity of the ball after the impact. And then when I use conservation of angular momentum on a fixed axis, what I did is that I was on an open stance, and when hitting the ball, I placed my shoulder at the fixed axis since I wasn't moving my body at all. And here in the equation, I represent that by here, as you can see, the moment of inertia about the fixed axis, which I told you was the shoulder, where this is the moment of inertia of my arm plus my racket, plus the mass of the arm times the head speed times the radius of center of gravity, which for the purposes of this test, it was my elbow, which was equal to the mass of the ball times the velocity of the ball times the radius of impact, which was from my shoulder to the straight spot of the racket. Okay, so as I told you, I figured out that I could increase the moment of inertia by setting the axis to be my left leg. So I will be rotating using my whole body over this fixed axis, and then I would have more moment of inertia at the moment of impact. So I figured out that by doing this, I could use my energy more efficiently, and also I could add more power to the ball. And that's how I solved the problem of getting finally the ball over the net. And you're gonna see the results in the next video.